So for instance, partitioning is not supported, but you could figure out a way to roll your own. It would be great if there was an engine enforced way to do that, but we don't have it yet. And I have no idea if items in this slide that don't have an asterisk or the subsequent slides for unsupported will ever be supported in future versions. But I think that Microsoft wants to deepen the strong footprint of this feature. You can't use truncate, you can't use snapshots, compression, and this can be a little tricky for migrations because if you're migrating from a table that is compressed, you'll obviously need a lot more storage in memory to support the same data. Things like that. A number of other things. One of the things that may really trip you up is there's no cross-database queries or transactions. So if your application depends on that, you probably can't work around it, then in-memory is not going to work for you. I don't know if it'll ever be supported, but it's definitely not supported in 2014, 2016, and as far as I know, 2017. FILESTREAM is listed as unsupported. There is some confusion about that, which we'll drill down into in a moment. And there's some things on the indexing side that are also not supported. Some of them are not needed, like include, you don't need, because all indexes are covering. And some data types that are not supported, but there are workarounds. There is a blog post from Microsoft about SQL variant, and I'm sure you wouldn't have to be a rocket scientist to figure out how to deploy date time offset, but at this time it's not supported. UDTs are easy to migrate because you just make them the base data type, but UDTs themselves are not supported. Just to get to FILESTREAM, as we said a moment ago, the 2014 release used FILESTREAM to manage all of the files that persist your durable memory optimized data. That was a performance bottleneck, and they redid the architecture for 2016. FILESTREAM is still used for what they call container management, meaning the folder itself that holds those files, but you do not have to enable the FILESTREAM feature in order to deploy in-memory OLTP. I want to be clear about that. And the FILESTREAM feature is definitely not supported, as we said in the other slide, for memory optimized tables, but it is supported in the same database for hard drive based tables. So it is possible to have FILESTREAM enabled in the database, but just not used for in-memory. Just wanted to be clear about that. Why now? Some people would say, why did Microsoft come out with this feature in 2014? Part of the answer is historical. CPU speed has been flat for ages now. Chip designers simply just place more cores on a given processor. But if your workload is not CPU bound, that's not going to really help you. The ever falling prices of memory per gigabyte. This is a 35-year spread here, and you can see that it is dirt cheap to get gigabytes of memory today. And latency. Latency for any kind of storage is significant. These are traditional hard drives that we lived on for decades. 10 to 20 milliseconds latency average. Then you have SSDs with a SATA or SAS interface, which is 10 to 20 times less latency. Then the PCIe version of, let's say, an NVMe drive, also 10 to 20 times less latency, but that cannot touch the speed of memory. Now, I want to be clear that for your write-intensive workloads to persist durable data, you will not get 100 nanosecond latency because you have to write to the transaction log. But for queries, you might approach something like that. Improvements in SQL 2016, pardon me, there are many, many improvements. I have here it listed in italics that there is no data limit per database, but that depends on the edition. There used to be a 250 gigabyte per database recommended limit from Microsoft. During the CTEs for 2016, that was listed as 2 terabytes per database. But right after RTM, or right around RTM for 2016, Microsoft has stated that there is no memory limit per database up to the operating system supported limit, and then they came out with SP1 where it reduces the amount of memory optimized data and column store by additions, and we'll do a deep dive for one of those additions just to make sure you have clarity about that. There's a lot of changes for 2016. They really did a tremendous amount of work. In 2014, you couldn't alter a table, you couldn't alter a procedure, you couldn't alter an index. It was really kind of carved in stone. Okay, let's see. Environments, it runs, of course, on physical hardware. It runs in SQLDB in Azure. It's going to run on Linux for SQL 2017. I myself have not investigated Linux yet, but I intend to because it supports In Memory. We'll do a Deciphering Editions deep dive now. The limits, not just for In Memory, but there are other limits by edition. And for In Memory, it's specified as max data or CCI, meaning clustered column store limit per edition. So standard says 32 gigabytes and 32 gigabytes, but as usual, the devil is in the details. Some of these limitations are per database, some are per instance, and this is where the details lie. For 32 gigabytes of standard edition, you can have 32 gigabytes of memory optimized data, and that is a per database limit. But for column store, it depends. If column store is on a memory optimized table, it counts towards the per database limit. Therefore, you could not have 32 gigabytes of memory optimized data and 32 gigabytes of column store data in the same memory optimized database. You could have a total of 32 gigabytes. And for a hard drive based table, it's the opposite. It counts towards the per instance limit, the column store limit. Subtle but critical. Recovery model is something that trips up people that are new to In Memory. So I want to make sure that we have clarity about that. The recovery model is irrelevant for memory optimized DML. Your inserts, updates, deletes, let's just leave it at that. I won't talk about merge. They're all fully logged if your table is durable, because 2016, or rather memory optimized tables can be durable or non-durable. And anything that is durable, of course, has to be logged. So therefore, in terms of DML, for durable memory optimized tables, the recovery model does not matter. Just a quick comparison for some of the aspects between hard drive based tables and in-memory tables. Durability is mandatory for on-disk tables. I don't mean TempDB, I mean a user table in a user database. You will have durability for your data. Durability, as we said a moment ago, is optional for In-Mem. Hard drive based tables are stored on pages and extents, and those don't exist for In Memory. There are streaming types of files that persist your durable memory optimized data. T-SQL for hard drive based tables is always interpreted, but for In Memory tables can be interpreted or compiled. Isolation is enforced via locking for hard drive based tables and is enforced via validation for In Memory. It's a completely different engine. Deadlocks are possible because locking is possible for hard drive based tables, but deadlocking is impossible for In Memory because there are no locks taken. I'm sure there's a virtual cheer in the DBAs that are attending this webinar. The objects that can be memory optimized are tables, table variables, functions, stored procedures, and triggers. It is possible to select from a hard drive based table and join to a memory optimized table. There does not have to be a separation. I should say, if you're not using native compilation, you can do this. You can use regular interpreted T-SQL, known as interop, and you can select from both tables, assuming that the requirements are met for isolation. This feature is optimized for highly transactional workloads, data loading, data ingestion, and transient data. It's not optimized for analytical data, although you can create a clustered column store index on memory optimized tables, and you might get a benefit from doing that. This stuff is designed to get data in your database fast and manipulate data fast. I want to touch on this. I've seen several posts in forums of people trying to do a proof of concept, and they were kind of lost about how they did it. They would, for instance, compare the results of selecting from a natively compiled store procedure from a table that had one row, and they would benchmark that, comparing it to it selecting from a table on a hard drive that had one row, and this will not float your boat. You need to have a reasonable amount of concurrency and complexity for in-memory to shine. And the tools that you use to test with concurrency, let's say one guy was using OStress, he was outputting to files on a hard drive, and that slowed his in-memory throughput so much that it was slower for him than his hard drive-based workload. So you have to be smart about the tools you use to test this stuff. Under the right conditions, it's orders of magnitude faster than the traditional SQL Server database engine. But testing with one row in a table is not going to make it for you. What you would like to see in your workload is that it would have all of these things as aspects. Your workload may not have high concurrency and high write activity. You may be bound, your latency may be due to the fact that changes for indexes are always fully logged for traditional tables. So logging has been redesigned for in-memory and many other things, and in combination, all of those things that were redesigned can equate to a huge bump in performance. So just to be clear, if you don't have all of these characteristics, it doesn't mean your workload won't benefit, but if you do have all of them, you're much more likely to benefit. If your latency is due to the engine, this is one of the main use cases and one of the main problems that in-memory solves, because the engine for traditional tables has to lock and latch and uses spin locks to back off, and none of that exists for the in-memory engine. So if you were constrained by the engine itself, then you have a good chance to have much better throughput and low latency with in-memory. If you have very complicated stored procedures that are constantly reinterpreted and therefore raise your CPU usage very high, then native compilation, assuming that you can use native compilation because the surface area is not quite at par with non-compiled T-SQL, then you could get a benefit from using much less CPU. Logging, as I said, is totally redesigned. We, in the memory optimized world, do not use any write-ahead logging. Writes are only, the transaction log is only written to upon commit. You do a begin tran, you do all your writing to your database, nothing is written to the log until commit time. That's a big difference, so there's no undo. What has to be logged is logged more efficiently, and there are no changes to indexes, and I have an asterisk next to that because that is 2/3 true, but for today's session we're going to say that's completely true. And if your latency is due to TempDB and you've already optimized the file layout of TempDB such that SGAM, GAM, and PFS pages are not an issue or less of an issue, and you still have contention on other parts of TempDB, well, temporary objects that are memory optimized don't use TempDB at all. You need better performance, and in-memory can help because of all of these things: lower CPU, less logging, no logging, and temp object replacement. And if you need to scale your workload, the fact that there's no latching, locking, or spin locks will allow you to get much better throughput. Lock-free, we have lock-free tables and index structures, completely lock-free. But that does not necessarily mean that it's not possible to wait on something. It is possible to wait on writing to the transaction log. It is possible for transaction A to depend on transaction B, and if transaction B has not yet committed, transaction A cannot commit. In the in-memory world, transactions can be dependent upon each other. These are usually very short durations, probably not going to be an issue, but it is possible. So I mentioned that for the sake of full disclosure. Your use case is you need high throughput and low latency, and assuming that your workload fits the layout that we talked about before, you don't have cross-database transactions, etc., you can achieve that within memory. Caching and session state is really the only use case that was available in SQL 2014, in my opinion. That's why adoption was kind of low. If you need to absorb tons of data from millions or thousands or hundreds of thousands of devices, you have a lot of Internet of Things these days, then this can be a great use case. We talked about TempDB object replacement can also be a great use case. And ETL, I know many people who have said that In Memory has has optimized their ETL loading process so much it's unbelievable to them. Concurrency is the lifeblood of In Memory, and the way it goes about it, we should contrast a little bit to hard drive-based tables. For hard drive-based tables, there is an optional database setting called read committed snapshot isolation or snapshot isolation, and it creates row versions in TempDB, which solves readers and writers from blocking each other, but writers can still block writers. For In Memory, we have an optimistic concurrency model. All In Memory tables are creating row versions if you make changes to them. Those versions are stored in memory, so you have to have enough memory to do that, which means it affects your capacity planning. This solves not only readers and writers from blocking each other, but also writers and writers from blocking each other. If your data access pattern for your application is such that you have many processes concurrently trying to update the same record, only one of them can win and the others will fail. And that's what we would call a conflict. So if your workload has excessive conflicts, you won't be able to get the throughput that In Memory is capable of, because it'll constantly be just accepting the first commit and rejecting all the others. If your application connects and runs very short procs, you won't be able to make use really of native compilation. And native compilation is not always required to get great performance. It just can be the extra oomph that you could get. And you might not think that resource issues could be an issue here, but storage and IOPS can be required in capacities that you didn't think would be necessary for a memory optimized based workload. When you remove the engine as the bottleneck, often you see that write log is either your top weight or close to the top weight. There is a solution for that, which we'll talk about next week, but your transaction log will receive much more throughput now, and it has to be able to keep up. And the files that persist your durable memory optimized data, the volumes that they reside on, have to have more IOPS than just the workload IOPS, and we'll get to that a little later. Of course, we must discuss memory itself, because that's the thing that keeps this going. Physical memory is divided amongst the operating system, and in this case, let's say for a dedicated SQL Server max memory. SQL Server max memory is divided amongst many things: the buffer pool, the procedure cache, the log cache, other data structures, and of course, in memory. So I want to be clear that the allocated resource, meaning memory, for In Memory OLTP does not come from something outside of SQL Server max memory. It's not a separate allocation at the operating system level. It's part of the max memory setting that it comes out of. Not advertised as a whole database solution, In Memory is not, but given the capacities that are available in Windows Server 2016, 24 terabytes, I would think that that would handle just about any OLTP database on the planet. I could be wrong, but you may want to consider putting your whole database in memory. I'm not. You'd have to check with Microsoft to make sure that's supported. I'm sure, pretty sure it would be, but there are reasons you might want to do that. The basic architecture is you have a database which has a special memory optimized file group, which is logically associated with one or more containers, and that's the FILESTREAM component we talked about earlier. And in this case, a container is just a fancy name for a folder. And within those folders resides the data and delta files that persist your durable memory optimized data. There is no possibility to limit the size of those files or the folder or the file group, so you have to have enough free space on the volume where your containers reside to grow. Another way to look at it is you will always have a primary file group, and now you have this special memory optimized file group associated with the objects we just discussed. And whenever something occurs that is written to the transaction log that pertains to memory optimized data, there's this background process, this checkpoint thread that harvests those events from the transaction log and writes to the data and delta files. There's a one-to-one relationship between data and delta files. A data file stores distinct ranges of transactions, and a delta file is a way to logically delete an entry in the data file. It's much faster to just associate logically a delete than to go into that data file and remove actual data. This has storage footprint ramifications. You can see this middle set of files has the 201 to 300 has a large number of logically deleted rows, and that will cause queries to slow and your storage footprint to grow. And there's a process to clean that up, which we'll get into in a little bit. Data and delta files are also known as checkpoint file pairs. This is kind of what they look like. Not really intelligible to human eyes. They're all stored with some GUID name and in a folder. You should never touch this folder. You should never manipulate these files. The engine takes care of this stuff. The basic durability workflow would be to update, in this case, update a row in memory and commit, and therefore it's written to the transaction log. And then the checkpoint will harvest that from the transaction log and write to the data and delta files. That's a kind of 10,000 foot view of how it works. Just like hard drive based files and hard drive based tables, instant file initialization is critical. It's critical that you configure it. Otherwise, the engine will be zeroing out all your data and delta files when they grow, when they're created for restore, etc. You don't want that to happen. So you must configure IFI. And a data file is shared. All these data files are shared amongst all of your memory optimized tables. So it's not possible to assign a set of files to a different object. And a given data file, the first entry can be from table 1, and the next entry can be from table 2. Before about currency and versions. I'm going to be clear that there's a lifetime for a version, and that is begin timestamp and end timestamp. It's also in pointers, and that kind of process the error. This is a version. Then you call it payload, which is data itself. This is a kind of poor man's rendering of what it might look like. A version 1, is residing at a location in memory, which is pointed to by an entry in an index. So you need to traverse, the engine needs to traverse an index to find a row version. There are massive misconceptions about which types of DML creates row versions. I have seen Microsoft official documentation and presentations, other speakers around the world, blog posts, get it wrong. So today we're going to nail it. Of course, an insert will always create the first version of any row. But a delete, we're going to cover that now. A delete, as we said before, to delete something, you have to have something already have a version. So let's say version 1 exists and you have this begin timestamp value and the end timestamp value is infinity. It's not set because this version is live. A delete will place an entry into the delta file, and then it updates the end timestamp for that existing version, and that's all it does. A delete does not create a row version. So now you should be able to share that with others. An update has to also update an existing version. So there's something that exists today, now I should say. An update is handled as a delete plus an insert. We know that an insert creates a row version, and we know that a delete does not create a row version. So it should be simple. You have an existing version, it gets logically deleted, the end timestamp gets updated, and then you insert a new version, and at the end you have created an additional version. So updates and inserts are the only type of DML that create row versions for in-memory tables. When those row versions are stale, when they're no longer needed, they have to be cleaned up. So that's what garbage collection does. There's various types of garbage collection, and one of them is for row versions. It is a background process. it's self-throttling, and it is cooperative, meaning that user activity, it does the bulk of the work. The purpose is to identify rows that are stale, row versions that are stale, unlink them from indexes, and schedule the reclamation of the memory they consume onto a scheduler. A user query would perform a partial scan of an index, and during that partial scan, it would identify versions that are stale and unlink them from all relevant indexes, and then place them on a scheduler. And when the user query is finished with its own execution, before it jumps off the scheduler, it checks this list to see if there's anything it must deallocate. And that's the basic gist of how garbage collection works. What can hang up garbage collection is, of course, a long-running transaction. That's bad for any database system. Also, if you cancel the transaction, just because you didn't commit doesn't mean that row versions just magically disappear instantaneously. They still, if you created row versions by virtue of your transaction, you updated 10 million rows in a memory optimized table, but you didn't commit. You created 10 million row versions and they have to be cleaned up. Table variables are not acted upon by garbage collection. So table variables, the memory that's consumed by them only is able to be reclaimed when the variable goes out of scope. That is a key difference between table variables, memory optimized table variables, and also memory optimized tables. And the DBA has no control over this stuff. Garbage collection just works. Now, just because, go back 1 second. Just because garbage collection is not operational doesn't mean it's not working. It needs memory pressure and user activity in order to work. So you could have row versions sitting in memory that are stale, but there's no need to clean them up now. So they're just there, they occupy memory. I want to talk about what I refer to as the memory dance. Let's say for a moment that you're not running enterprise, that you cannot use resource governor to create a resource pool. And that would be used to constrain the memory associated with a memory optimized database. Let's say you're in standard and you have some data in memory and you have some data for your buffer pool. And now you add rows to in memory and the footprint wants to grow and it puts pressure on the buffer pool, and the buffer pool reduces its footprint. And that's one way the buffer pool can be shrank. And now let's say you deleted rows in memory and the buffer pool wants to grow, and it can grow. But what if your in-memory grew and then you didn't delete anything or didn't delete anything in long enough, for a long duration? Then the buffer pool shrinking, assuming you have a traditional hard drive based workload in your memory optimized database, your hard drive based workload performance can suffer greatly. You will wish you were on enterprise in order to use resource pools in this case. Smart attendees might think they can use the buffer pool extensions, and you could in standard edition, of course, but buffer pool extension performance is not good. It's single threaded, one 8K page at a time, and as a result, you may see a performance slowdown with your hard drive based workload that is insurmountable. If you think you can use some form of compression for your in-memory footprint or paging, you cannot. It needs whatever amount of memory it needs. You need memory for data, indexes, the growth of those data and indexes, row versions that would be created during your workload, table variables and their row versions, and temporal is a new feature in 2016, which also can be a silent memory consumer, because the implementation that Microsoft did was there's a secret hidden staging table that also resides in memory that gets flushed to the history table on disk when it reaches 8% of the temporal memory optimized table size. That could be a lot of memory, a lot of rows, and a lot of consumption of memory that you could use for other things. So that's a potentially silent issue. We said that there's different types of garbage collection, and one of them is for the files, the data and Delta files that we spoke of before. Take this example where memory optimized workload the engine decides that, okay, these two sets could best be combined into one. It would reduce the query time, it would reduce the storage footprint, and it identifies an adjacent set of checkpoint file pairs to merge. And it merges them into one set, and that set encompasses the range that was formerly occupied by two sets. This occurs in the background. You have no control over it other than you can initiate it, but it occurs naturally through the engine. And these files must go through a number of transaction log backups and checkpoints in order for a file to actually be removed. Therefore, your storage footprint can be larger than you might think and for longer than you might think. As I said, you can force file merge with this very long system procedure. Storage, Microsoft recommends 4 times your durable in-memory size. That seems like a lot, but again, that's because those state changes don't occur immediately, and your volumes need to have enough free space to grow. So you need your initial footprint, room for growth. Your backups can be larger because of those state changes not occurring immediately for your data and Delta files. And your workload I/O needs to be, the drives need to be fast, and of course these are streaming files, so they're written to sequentially, so sequential throughput would be great. It's fast sequential throughput. I wanted to take a sample migration here, an example of this. We would have customers and orders, something really simple, and we're going to try and decide how this sample migration might work. Where should we put the customers table? Should we put it in memory, or should we leave it on disk? We want to have hot orders in memory and cold orders on our hard drive. So in order to not leave orphans in the orders tables and to not insert or update a row in orders that would relate to an invalid customer record, a parent record, we need to have some type of foreign keys or triggers or some kind of logic that handles that. Usually this is done with foreign keys, and you can do this kind of foreign key between the memory optimized tables. It works. If you want to do it from a hard drive based table to a memory optimized parent, it cannot work. If one side of the foreign key is memory optimized, both sides must be memory optimized. So we'll try another approach. That would be, we know we can do this, which is a foreign key between memory optimized tables. We'll try a trigger from a hard drive based table to a customer's table in memory, and that will work. So we've solved 2/3 of our issues, but we need to make sure that if we delete a customer, that we don't have an issue with in the cold orders table leaving an orphan. And we'll try to create a trigger going from the customer's table in memory to the hard drive based cold orders table, and that fails because, again, a trigger on a memory optimized table can only reference memory optimized tables. You could try then to put the customer's table on the hard drive, and this tried and true foreign key, of course, will work. We know we can create a trigger from a hard drive based table to a memory optimized table. And for your DML, you could create what we call an interrupt, a regular interpreted T-SQL procedure that any change to an order verifies that a customer exists. So it's not an engine enforced, it's a user enforced piece of logic that could solve the problems of orphans and parent-child relationships in this case, but I would like to see an engine enforced way to do this, but at the moment there doesn't exist such a thing, so you have to roll your own. Some people might think you can use temporal to solve this problem. In my opinion, you cannot. If you did have a set of temporal memory optimized tables, then the history tables would track that relationship over time, but 5 years from now you'll still have 5-year-old customers and 5-year-old orders in those temporal memory optimized tables, and that's not what I call a hot and cold solution. I wanted to briefly go into this utility that Microsoft supplies us. If you right-click a database and choose reports, you can either see transaction performance analysis overview, or you can find it under standard reports and then transaction performance analysis overview. And that takes you to something like this, where you could click on Table Analysis. And in this case, it's showing me that in this magic quadrant that the audit trail table will have significant migration work because it's on the left side, but it will have a high gain because it's towards the top. And if you trace this query that is executed, I believe this query has not been updated for SQL 2016, so I would not trust this report. Microsoft comes up with a number, a migration rating per table that determines tries to illustrate to the user how difficult it might be. But the things that it checks, if you look here, the things that it checks are, of course, performance stats, etc., locking, latching, but it also checks, it counts the number of nullable columns, lob types, and unique indexes and constraints, and these are completely supported in SQL 2016 with no issues. So I don't know why they count them, but they do. So I don't trust that. I rolled my own version of this, which I'm happy to supply to people, which lets me know, we'll run it here, lets me know the locking and latching in the top results set, and lets me know how many potential issues I might have and exactly which kind they are, because a default constraint is a breeze to migrate, but foreign keys may be really difficult to migrate. UDTs are super easy. So you can't always trust the Microsoft tool that informs you or attempts to inform you about how easy or difficult it is to migrate to memory optimized workload, migrate your memory optimized workload. Planning would be, you would identify your bottlenecks, you would try and determine if in-memory might help solve those bottlenecks based on what we discussed earlier, and you would do a reasonably good proof of concept to determine, based on the hardware you might be running on, if in-memory will really raise your workload throughput. From a capacity planning perspective, you need double the in-memory size that you would start with, and that's because Microsoft does not know your workload. If your workload is insert and delete only, and therefore you're only ever creating a single version of any row, you won't need as much memory to execute your workload as if your workload was also including updates, because updates create additional row versions. So Microsoft suggests 2 times your in-memory size and go from there. For IOPS, let's say your workload IOPS required are 500. That's for your regular workload to populate the data in Delta files as your workload is occurring. But to merge the files, depending on your workload, to merge the files in the background, that's a background process, you need additional IOPS to read and additional IOPS to write. So you need, according to Microsoft, 3 times your workload IOPS from your storage. And that's a part of the memory optimized world that's not really intuitive to people. And as we mentioned earlier, your storage footprint should be considered to be 4 times the durable in-memory size. Obviously, if you're doing ETL loading and your tables are not durable, you don't need to plan for 4x, whatever your non-durable memory optimized size is. These are some of the types of capacities you have to plan for. I want to briefly go over the white paper, because the white paper was great when it's still great, but it was submitted probably a month before RTM for 2016, and by the time RTM came out, it was already dated. There are some inconsistencies there and some things that are no longer true, so I want to review those because people who are planning to adopt in-memory will likely read this white paper. It says that indexes are never stored on disk, and that is true for hash indexes and for range indexes. It is not true for clustered column store indexes. Clustered column store indexes on memory optimized tables are persisted to disk. It is done so as to speed recovery, because remember, because hash and range indexes are not persisted to disk, they must be recreated on the fly. But to recreate a column store index on the fly during restore, or if you're offline online your database, can be a very expensive process, especially if your memory optimized tables are large. So Microsoft does persist custom collared store indexes for memory optimized tables to your data and to your data files, I should say. The white paper says delete and update operations will generate row versions. Well, we have debunked that myth. It is, in this context of this statement, it is only update operations. Of course, inserts also create row versions. It says data is on your disk to be used when restarting your SQL Server. That is correct, but not quite complete, because anytime your database is restarted and therefore needs to be recovered, all of your durable memory optimized data that existed has to be restreamed to memory. And I'm talking about things like if you simply change your database from read only to read write, or the other way around, it will restream all of your data. If you set read committed snapshot isolation on or off, it will restream all your data, in addition to failover, things like that. So anything that causes your database to be restarted is the reason that data is persisted. There were various statements in the white paper about the number and size of data and Delta files created based upon memory and things like that. I'm sure they were true at the time, they're just no longer true. It said accurately for the time that there was a 2 terabyte per database limit. It was true then, it's no longer true. Now, as we said, it's based on addition and your OS max capacities. There's a conflict in the white paper about parallelism is supported or it's not supported. It says both. And it is supported for many and most things. All index types support parallelism. Tables and variables can be scanned in parallel, the heaps in memory themselves. Sampled statistics can be done in parallel. And if you have a merge statement where the source of the tables, not the target, but the source, are memory optimized, that can occur in parallel. But things like native compilation itself never uses parallelism. It's always single-threaded. And if, for instance, you had a memory optimized table as a target of a merge statement, it could not be, you cannot insert in parallel or update in parallel. For SQL 2017, we do have some changes, as we mentioned. The max indexes ceiling has been lifted. Right now it's 8 non-clustered indexes per table and 1 column store index, 1 clustered column store, for a total of 9. That's up to and including SQL 2016. 2017, I actually created a table that had 300 indexes, I think it was, and it succeeded. So I believe it is the same exact limitation as whatever the hard drive based table maximum indexes are per table. We said a moment ago that in order to rebuild your range and hash indexes on the fly, that this can be an issue for recovery. And Microsoft has redesigned how that is done. And so they say for 2017 that, I'm sure they did this because now they support way more indexes. It would take forever to recover your database if they didn't optimize the process, that there's an index rebuild speed improvement for non-clustered indexes. Computed columns arrive in 2017, and you can create indexes on those computed columns. You can finally rename tables and native modules. That was sorely lacking until 2017. Space used returns correct information in 2017. Hard drive based tables have had parallel redo for AGs since 2016 was released, but not for memory optimized tables. And now we get that in 2017. And for T-SQL itself, we now have case, JSON, and cross-apply. The key takeaways for today are workload evaluation, use cases, and how architecture of your database needs to change and affects other things in your database ecosystem from deploying in-memory OLTP. And with that, Ami, I can take any questions if there are any.
Yes, wow, that was really good, Ned. I've heard a few talks about in-memory OLTP. This was definitely one of the best. Good work.
Oh, thank you so much, Ami.
So we have questions. So Christian asked, will this customized migration script will be available later, the script that you customized for 2016?
I can send it to you, Ami, and I assume you can make it available. Or I can post it on my blog, either way.
Even better if you post it on your blog, other people will.
Okay.
Yeah.
I will post it on my blog tonight. There are some kind of loose fitting comments in there. and I tried to identify the things that I went through really too briefly in this presentation.
Okay.
I'm fairly descriptive in there. If anyone has any questions, once they upload it, they can just ask me.
And your blog address is here on the slide, nedotter.com. Okay.
That's correct. I have a lot of posts there about In Memory that dive fairly deep into some of what we talked about today and other things that we'll talk about next week and other things that I don't have presentations for yet.
Okay, great. So we had some audio issues during the session, but it was brief. It was like for less than a minute. So we had a few. That's for all the people. Yes, it wasn't just you, it was all of us. Dennis asked, what tool would you use to POC this feature for a highly concurrent workload? Lots of writes, the same record multiple times, and short select calls at the same time.
Okay, so let me answer the first part first. Which tool? I would use OStress. I like OStress, but you cannot use it when in a way in which it writes output files of the progress to your hard drive. So there's a flag to do that or to not do that. And I have a blog post exactly about how not to benchmark In Memory OLTP on my blog. So I list the specific case. I don't think it's possible, if I understood the second part of the question correctly, I don't think it's possible for In Memory to do a great job with a record that is concurrently updated by many dozens, hundreds, thousands of processes. Because of what we talked about before, there'll be no blocking, but you will have conflicts and all of the other processes will be rolled back or will fail to commit because of a validation error related to isolation. So I don't think that type of workload data access pattern is a good fit for In Memory.
Okay, question number 2. You mentioned that short calls would not be a good fit for this feature. Could you please explain why?
Okay, just to be clear, short calls would not be a good fit for native compilation. All the rest of your workload may benefit from all of the other aspects of In Memory, but in order to get a benefit from native compilation, and there's going to be a trade-off probably because it doesn't support the full T-SQL surface area, in order to get the benefit, your store procedure or function or trigger must be reasonably complex. If it's really short, it means it wasn't complex. So by definition, so that's what I meant. You can still have fantastic performance gains from using In Memory and not using native compilation. I want to be clear about that. So native compilation would be maybe the icing on the cake, but you can do great without it.
Okay, great. I think that answers. And both Dennis and Brian commend you on your excellent talk and amazing info. So
thank you.
Yes, if there are no other questions, I think we can wrap it up for today. And remember, don't miss, this is just part 1. The good stuff's coming next week, right, Ned?
That's right. Next week is more about what you can expect as a DBA to run into managing an environment that contains memory optimized databases. There's more to it than you would think.
Wow. I'm expecting that. Thank you very much, Ned. You've been great. We'll see you next week.
Thank you, Amir. I really appreciate it.
Have an excellent rest of your week. Bye-bye.
Thank you, you too.